All right, our next learning objective is about kind of where functions are not going to be differentiable. All right, so this figure to the right is f. It's a vertical tangent at 2, horizontal tangent at 4. Which of the following statements is false? All right, so it's not differentiable at -1 because there's a jump. All right, that's definitely true. It's not differentiable at 2 because of vertical tangent. All right, that's one of the reasons we learned is not differentiable. It's not differentiable at 4 because of horizontal tangent. Well, that doesn't seem right because a horizontal tangent just has a slope of 0, which means it does exist and it's just 0. And it doesn't exist at 6 because of removable discontinuity. So that's actually true. All right, so the vertical tangent is specific to derivatives, and then the jump and the removable discontinuity are you can't take the derivative if it's not continuous. So those ones are actually true, which means C has to be the right answer. Which of the following statements about the function, if true, cannot be used to conclude that f is defined at -1? So we're looking for when is f defined at x equals +1. Well, if f is continuous, there's 3 parts of being continuous. The function exists, the limit exists, and those things are equal. So knowing it's continuous is enough to know it's defined because that's one of the definitions of continuity. All right, so 1 is true, so it can be used, so B is out. If it's differentiable, we just saw in the previous problem, if something's differentiable, it has to be continuous, which means if it's continuous, that happens, so C is out. All right, the tangent line exists. Well, if there's a tangent line, there's the slope of a tangent line, which is the derivative, which tells us it's continuous, which tells us f prime exists. All right, so the only thing that's not enough to know if f is defined is just knowing the limit exists, because we could have a graph that looks like this. All right, the limit exists at this point, but the function does not. All right, so just knowing the limit is not enough to know that the function is defined. All right, but the other 3, tangent line implies there's a derivative, derivative implies it's continuous definition says our function's defined. And here, for this graph, for which values of x is it not differentiable? We've said it a lot so far. When it's not continuous, it's not differentiable. So 3 is automatically one of the answers. But with derivatives, we have another place where they're not going to be differentiable, and that's just any sharp corners or cusps. And we have 2 sharp corners here at -2 and 0. So D is the right answer. And for 16, create a graph where it's differentiable everywhere except -2 and 3. So basically just draw a continuous graph that has problems at -2 and 3. So we can use that previous example as our motivation. At -2, we could have a cusp, and at 3, we could have a cusp, and then just make it nice and smooth from there. All right, smooth curve down there, smooth curve, all right, with real sharp corners at -2 and 3. Another option would just be kind of draw straight lines with jumps, because we know at jumps it's discontinuous, so that would be differentiable everywhere except for where the jumps happen at -2 and 3. You can mix it up. You could do a real sharp corner at 2, and then an asymptote at 3. All right, there's infinite options. I just know the ways that it's not going to be differentiable: sharp corners, asymptotes, if it's not continuous, and vertical tangent lines, which might be the hardest ones to do, but again, you could do it. All right, vertical tangent line at 2, vertical tangent line at 3 or something. All right, so there's a lot of options for how you can do this one. Some might be simpler than others, but if you know how when a function is not differentiable, just put those on your graph at the specific x values. All right, make sure all the other values are not problems. All right, this one is about the power rule. All right, so if we have this piecewise function, what is g prime of 1? All right, so piecewise are always a problem when you switch piecewise, or switch the different rules. All right, so for this one, if we take the derivative to the left of 1, we're going to be taking the derivative of this function. All right, that's not correct notation, but just saying about me. So if I take the derivative at the top, I'm going to get -2. All right, so the whole time I'm before 1, my derivative is -2. After 1, the derivative of the bottom function is going to be 5. So everywhere to the left of 1, I'm going at a rate of -2. Everywhere to the right of 1, I'm going to a rate of 5, and that's going to look like that. And there's going to be a cusp at 1. All right, slopes of -2 turn into a slope of 5, and that means you have a cusp, so this is non-existent. All right, if these two things turned out to be the same number, that would be the answer, but they're different numbers when I switch my piecewise, which means it's not going to work. All right, for number 18, this looks like a really complicated problem, and you could just work this whole thing out by hand. All right, just like you would have done in the first learning objective, and you'd get an answer. All right, but this one you can actually simplify a bit. This is x plus h being squared. This is x plus h being multiplied by 4. And this is subtracting x squared plus 4x. All right, so this is the derivative, or sorry, the limit definition of the derivative for x squared plus 4x. And we can use the power rule to quickly see that answer is 2x plus 4. Again, you could just solve this all by hand. It's going to take you a little bit more time, but if you recognize this is just the limit definition of x squared plus 4x's derivative, then you can just do the power rule and save yourself some time. So nothing wrong with doing it the long way, but if you can recognize a shortcut, it'll save you some time. All right, 19, we have x to the 1/4. We want to find f prime of 16. So this is 2 steps. First, we have to find f prime of x. Using the power rule, the 1/4 comes down, and we subtract 1 from the exponent. So 1/4 minus 1 is -3/4. And now we want to plug in 16 to that. What I like to do when I'm doing these fractional exponents is I do the root part first. So anything to the 1/4 power is the 4th root of that. So what times itself 4 times equals 16? That's going to be 2. And then a negative exponent is 1 over the positive exponent. And 2 cubed is 8. And 8 times 4 is 32. All right, so this one's kind of half about the power rule and half about your ability to evaluate this expression with this negative fractional exponent. And then a short answer basically just uses a lot of power rule stuff all at once. So the first thing I would do is rewrite this as all of a bunch of powers. All right, just like we just saw, the 1/4 power is the 4th root. The cube root is the 1/3 power. And we also just saw 1 over a number is a negative exponent. Right, so now I can just use the power rule. Bring down the power, subtract 1. Bring down the power, subtract 1. X to the first, I'll just write it as x. Right, bring down the power, subtract 1. Bring down the power, subtract 1. Right. It doesn't say you should simplify anything, so I'd be fine with this answer. If you wanted to write it in a slightly nicer way, without negative exponents, it would look like this. Right, but not necessary to do. But this is how this negative exponent turns into that. That negative exponent turns into over x cubed. So just using the power rule, remembering that you can rewrite a bunch of different expressions as a power of x so that you can apply the power rule.